review report that you have to write, okay? So far right now is, I hope you guys do enjoy the lecture, okay? Yesterday, I already go ahead and then review all the feedbacks from you guys. So the midterm evaluation that you guys submitted, I appreciate, so we have 19 people, 19 students that take this class, and then out of 19, there's 10 that did the midterm evaluation, the Qigong Pingyang. And for each of these evaluations, I actually look very closely, and I appreciate those 10 students. Of course, I don't know who are those 10 students. They are anonymous, so you don't have to worry if you wrote anything terrible, okay? So those 10 midterm evaluations I have looked closely. Most of the feedback are very concrete, legit feedbacks. I really appreciate it. Hopefully by next year, once again I hope that this class can be better. So I'm counting on you for giving me feedbacks, okay? One of the feedbacks I got is he's wished that we have a field trip for this class. I think this is very legit thing that I think it's also aligned to what my curriculum for the future of this class. So in the future-wise, this class for next year, again, we might have a field trip, and we also will have a hands-on experiments to let you know what exactly about paleontology or paleo technology. Okay, so I think all of these evaluation feedback other stuff is if you look at Moodle, I already go ahead and then respond the comments for you that you have done for the first homework is the draft, right? The proposal, right? Is it proposal, right? So you just have to write a half-page proposal. So here's the thing, is that by the end of this class, in your Moodle, if I say that come and talk to me after class, meaning that you have to come to me and talk to me after class, this class I mean. So I want to talk to you about more detail about your draft, because I think it's a little bit more difficult for me to write a long paragraph to kind of help you understand what is the scope of writing this research, literature review, or whatever we say this is. So if I say come after the class and talk to me in your Moodle for your comment, come after the talk to me, okay? All right, I want to be clear with that. Second is that, again, doing this is by normal, meaning that if you submit, you automatically get 4 points, okay? If you don't submit, you get 0 points. Is that clear? So if you don't submit, you get 0. So it doesn't matter how terrible or how the quality it is. As long as you submit, you get 4 marks. So I want to make that clear. So by the way, if you submit late, there might be some consequences, but I still urge you to submit. If you didn't submit, still submit, okay? Because it will heavily impact on your score, okay, your final. All right? Any questions so far? Okay. Now, this is currently the agenda for this semester, and the reason why I can't show you this is that we have some revised or modifications. So I want to give you kind of what's going on. So we are right now into our week 9, right? So that's over here. So next week, on week 10, we will invite Dr. Wang. So he's currently a scientist at Modex 3D. So I don't know if you know Modex 3D. Basically, it's a software company that do injection molding simulations. I think so far, all the instructors that I have invited, most of them are very experimental based. This person, who's more simulation based, I think will give you some kind of grasp about how to do prediction and stuff. So I think it will overall benefit you. 11, week 11, 12, and 13 of the year, again, Dr. Cho will be back again to talk about powder. And then week 13 of the year, that's me talk about rheology, so quantum science. We'll see how this goes because since this is the first class that we're offering powder rheology, so I'm still kind of modifying the classes as time goes on. Week 14, we won't have class. So basically, week 14, the class is canceled. Okay? And the main reason for that is because week 15, you actually see this. Hopefully you can see. So week 15, this is a tone paper that's due. So this is whatever this, the paper you're writing, this is the cutoff date. So I'm giving you guys some grace on week 14 where there's no class, you can really work on it. Okay, so there's no excuse if you tone in late. If you tone in late, you get 0. So I think the tone paper is due. So on week 15, we have Dr. Chi. He's from Melbourne, Canada. He will talk about powder analysis. So powder technology, by the way. So we'll talk about all the machines you can do powder, how you analyze powder, the distribution, and all this stuff. It's all we have. Okay? And week 16, we have final, the comprehensive exam. More detail about the comprehensive exam, I'll talk a little bit more as our class goes on. So right now, I don't think you have to worry about it too much. So that's week 16. And week 17, we don't have class. So our class ends at week 16 when we have the final. And week 17, basically I'll sit in my office during that time, which is this time. And if you have any questions, if you want to know how much you got for your final or exactly the total amount of your scores, you're more than welcome to come to my office during that time. So after that, on week 17, specifically on 5, so our class ended at typically 4:30, right? So I'll submit the grade on week 17. On Tuesday, 5 o'clock. So, you can come in and then okay, so. Now, other stuff is, one thing I noticed is that, okay. So I noticed on Moodle, when you submit your page proposal, so next week is due for reference, right? Reference, 就是参考文献嘛，对。So I think there's something we need to really clarify is what's the, being consistent. So over here, I already stated that, so over here it is, you're supposed to put your first name, go ahead and do that. Your first name and your last name. Your first name and last name. And then this class, and it's called hello. Okay, so when you submit on Moodle, you're supposed to have this title on your paper. Okay, so next week, which you're supposed to submit a tone paper, right? You're supposed to submit your tone paper over here. What I'm supposed to see is again your first name, last name, and the class NB5401-701, and then reference. Okay, is that good? Right. So some of you actually received PowerPoint and Excel file. I think that's why the reason I asked you to come and talk to me after the class because I have no idea what's going on. So remember that. Okay. Question so far. 你看有没有什么问题？我跟你讲，格式很重要啊，不要搞笑哦。If not, so we're getting into today's class. So today I'll talk about fracture. So you might wonder why we are spending time to talk about fracture since this class is called paleontology or paleo technology or paleo science. So I think from every aspect of engineering, at a certain point, you deal with fracture, right? I mean, that's what we all engineering do, because we, on the other hand, want to know what is the strength of this material, right? You guys agree with me? So specifically, since we're in mechanical engineering, mechanical actually, if you go look at the check of the word, the actual fundamental is tied with stress and strain. So if you talk about stress and strain in mechanical departments, you then have to further think about, all right, what do we care the most? It's the strength,强度, we care the most. Because if we're not in mechanical engineering, perhaps we're in electric engineering, the most important we talk about is electric. It's a dumb question, right? So if we're in chemical engineering, the most stuff we talk about is chemistry, right? So in mechanical engineering, the most thing we care about is strength, strength. So the other way of saying strength is failure, or other way of saying is fracture. So there's a joke when I was studying my PhD is that when a person say that my specialty is in failure, it sounds a little bit weird. 就是如果你要问说你的专长是什么，我的专长是失败和破坏，就感觉好像让人家觉得你一生都在做失败的东西。所以通常就是在业界，他们不会讲说我是做 failure， 就是我是那个失败工程师，这样感觉很奇怪。我是做所谓的强度可靠性，对，所以这是另外一个说法。但是这边还是讲 fracture 就等于是另外一个说法是 strength， 一旦过了 strength 就强度，那 strength。Let me help you to review when I say strength. When I say strength, actually there's many points. It can be yield strength, it can be ultimate strength. 大家知道吗？当我讲强度的时候，有可能是有可能是指相互强度，有可能是指抗压强度，就强度是指哪一个 So anyway, strength is something we have to recognize. Now, FYI, when people, at least from my field, when people say strength, what do you think they normally refer to? Do they refer to the ultimate tensile strength or the yield strength? 就当有一个业界人他说，这个强度是这样，那你觉得他 refer 是在相互强度，还是指最大抗压强度？都是强度哦。你觉得他们往这 refer 是什么？这个我今天只要设了一个 poll， 我觉得以后有那种互动，其实是大家可以即时在那个手机上面直接点 yes or no， 然后就可以看那个 poll 出来的多少次。对，来，有没有大家觉得是什么？相互强度，还有没有别的？没有。有没有觉得是那个最大抗压强度的？有吗？有。OK， 有。OK， How about the international students? What do you think about when I say strength? When people usually refer to strength, you do know strength, right? Strength. Yeah. When people say strength, are they referring to ultimate tensile strength or the yield strength? What do they refer to? By the way, do you know the two difference? Do you know the two difference between yield strength and ultimate tensile strength? Do you know the difference? It's fine. If you don't know, just say no. You have no idea. You know? You have no idea. Great. You guys know? 等一下，你知道吗？我们今天人超少，知道吗？你知道最大抗压强度跟相互强度的差别在哪？你知道吗？不知道吗？So let me just quickly draw a graph. Actually, no, I'm going to use this. So supposedly this is a stretching curve, right? And then you have a metal, and then FL. You see that? So this at the peak is the ultimate tensile strength, and then over here is the yield strength. Clear? 清楚吗 ？Okay. So in industry， 在业界，当他们讲这个强度是多少的时候，他们都是指最大的抗压强度 （ultimate tensile strength）。OK， 那如果你要再确定的话，你可以讲说你的强度是指这个还是这个？I think you need to mostly industry they refer ultimate tensile strength, but you just have to double check. Okay, that's the important thing. So when people say fracture, they mean strength. there's no time involved, or small amount of time. Okay. So what does that mean? Small amount of time, no time involved. What does that mean? It is when I say fracture or failure, I'm meaning that something that's when I take this and then I break. Okay, this is instantaneous. Okay, if there's a time involvement, then that's a fatigue. So if there's a time involvement, it's fatigue. 如果有时间牵扯到的话，它就是疲劳措施。Okay, or maybe creep 浅变。Okay， 所以疲劳还有浅变这些there's some time involved. But when I say about fracture, meaning that's something that I just break. So take the most widely used example. If you review your Talos, your Material 101, Talos 的那本书在讲，最常讲破坏就是讲铁达尼号。The most usually used incident of titanium, when they smack on an iceberg, it fractured, right? So that's a fracture. There's no fatigue. When we talk about fatigue, normally it involved with time, an instant, a cyclic loading, a sinusoidal curve of a load. Now, if today if I constantly give a load like this, okay, and if I give a temperature and a constant time, that's called creep, 浅变. Now, if today, if this is, and I continue with this is fatigue, 就是浅变, okay, 所以这几个的概念啊，所以我这样把它就折断了，就是 fracture。 清楚吗？所以这有些概念要把它记清楚。Okay, so no time. So the fracture of things that break suddenly, as I already expressed. So the reason why kind of jumping back and forth is I want to again emphasize the importance for you. At least you guys are graduate students. Okay, at a certain point, maybe in the future, but now you're graduate students. You will at a certain point deal with fractures. It's inevitable. So you need to have some understanding what is the failure criteria, what are these materials attributes when you get this a load. So this is why I think it's especially important to talk about it. Okay. So these are some examples. On the left-hand side is Feynman. So this is a well-known physicist, Feynman. I think he was in a Senate science ruling. What happened right now, he's holding is a gas tube. What happened is at that time when we were launching a rocket to the moon, there was actually an explosion. So prior to the successful of Armstrong that landed on the moon, there was actually quite a certain amount of series of explosions of rockets. So he was trying to explain at that time, at the hearing, of the scientific hearing about the rockets that has somewhat some doctor that transferred to brittle characteristic. So 如果我们学工程材料，我们都知道有些材料就是有所谓的眼镜转瞬性的这个效果，对不对？我们都知道。Okay, so I think I won't get too much in detail. Actually, next slide I will talk about it. But this is again on the right hand side is a great example of a failure. So if you look at this, your instinct will tell you that is this a brittle failure or ductile failure? Is this on the right hand side? Is this a brittle failure or ductile failure? 延性破坏还是脆性破坏 ？Right? Any thought about this? 没关系，不知道答案都可以把它讲出来。我没有证明啊，所以没办法奖励，但是可以大声讲出来。我们学生现在人很少。你觉得是延性破坏还是那个脆性破坏？脆。So do you think this is a brittle failure or ductile failure? This brittle or ductile? Brittle. Okay, so it's a brittle failure. So there again, there's some attribute you can see, right? Because I don't know if you can see this is a straight cut cleavage, right? It cut very vertical cut, right? If it's a ductile failure, you can imagine like a plastic or rubber, when you pull down, there's supposed to be some string or some little lines that being pulled out. But interesting enough, you can see this phenomenon here. Same as an egg. These are also again not ductile failure, it's a vertical failure. And on the right hand side, this is a hot valve that is installed inside your hot here. And this is actually a composite material. There's a lot of definition over here, I won't get into detail, but interesting is that today we'll spend a little bit of time to talk about brittle failure. How do we get, how do we quantify these numbers more quantitatively, okay? So these are, again, some news in the past. Propeller blades or outer surfaces, you can see. I'm going to go ahead and jump to this. So this is a glass rod. It's being bent elastically, heating involved. Why doesn't it break? So actually what happened right now is actually what do we expect? So ceramic have a very large yield stress value, but at this point right now, if we bend the glass, if we really know material science engineering, we're actually able to manipulate its material properties that allow us to bend without brittle failure. Okay, so anyway, so glass and ceramic at very high value for yield stress, but they invariably will break before they bend. So while aquamarine will bend before they break. So normally when you see glass or ceramic material, if you draw a expression curve, what you see is that you have a fluid like this. This is what you hand out. So this is more of a ceramic material. And if you see metal over here, what you see is you see something like this. Okay? Clear? Okay. Now interesting is this over here, this kind of metal, normally is mostly under the condition that we're in normal temperature, right? If today we're at a very low temperature, do we still see this kind of phenomenon? No, right? Because the same instance in Titanic wasn't like this. It was like this, right? I also, by the way, I just want to clarify. I know there's some people that's not in material science background, but 我知道你都材料背景，那你知道就是盐基转萃析是什么意思吗 you guys know, right? How about on the back? Do you know? Are you a material background? 你是材料背景吗？机械背景。OK。然后是材料，你是材料背景吗？化工背景，然后 OK。材料背景 OK， 然后So I want to just give you some background. So 那 by the way， 那你们知道那个铁达尼的事件为什么他就沉下来？他那个整个 overall 的 story 吗？你知道吗？大同那个老师有好好讲吗 ？OK， 所以你知道，然后你知道为什么他那个吗？你也知道吗？我大同大概都会知道。那你知道吗？不知道。OK。So just out of here, do you know the incident of the Titanic? Why it failed? Like the Titanic incident. What happened? No, not exactly. Okay. Yeah. So for those that already know, just bear with me. Just how about let's do that. I think the version that you guys hear was basically Chinese Mandarin version, right? So how about here the version of English version? Perhaps can help you increase, practice your English as well. So I think what happened back in those days, Titanic was one of the very frontier technology that was made at that time. By the way, it wasn't a lame business book, by the way. It was the art of building a cruise that had all the entertainment and structured facility that was built. So at that time, when that was traveling its Virgin line through the Atlantic Ocean, that was its first travel. And unfortunately, it was that first travel, it hit an iceberg and it sunk in. Now, as a typical engineering, these kind of things isn't really normal, because if a typical metals, if you hit a iceberg in normal metal, what it responds is that you will go through a heal, and then normally plastic deform, and eventually you fail, right? But what you see on the instant of titanic, it wasn't really like that. It wasn't not ever like that. It actually shattered like glasses. And interesting thing, well, it's not interesting because it caused tragic of people that died on board. Okay, and it wasn't expected. Now, there's many causes that kind of pile up that rooted in this failure tragedy. But the overall was because at that time, Titanic was this version traveling to, I think it was to New York City at that time. And it was traveling along the route of Atlantic, close to what's it called? Greenland. So the place. Anyway, it's very close to the North Pole. And you have to imagine the water at that time is close to 0 Celsius. So you have ice floe flowing everywhere. So at that time, the investor was also on board. That boat actually carried a lot of famous scientists, actually also include the most frontier metallurgists and all these people on board. And the investor was also on that board, and then they talked to the captain, urging them to increase the speed so that they can arrive early on time to show that, oh, this boat not only is the frontier of any other boat that was commercial boat that was made, but at the same time, it also has great performances that can reach way before projected timeline. So that would be nice, right? If you take, for example, if you take the high-speed railway, and then it's projecting to arrive at 9 o'clock, and then you suddenly arrive at the station at 8:30, half an hour early. What do you think? Man, feels great, right? Right? So they increase the engine power. They push all they can, and then they start having this boat start running. And what happened is they saw iceberg, right? I mean, yeah. And then they try to avoid. So what happened is, you can see, let me see this stuff. So pretend this is a Titanic, right? And then you have an iceberg over here. So the crew member that's over here saw this iceberg, saw signaling, yeah, we need to land, but right, too late. What happened is they tried to avoid this. They did, okay? They didn't smash the iceberg like that. They actually tilted successfully. But unfortunately, there was a bump. They still bump in on the edge of the iceberg. Okay, so 这是擦撞，它是擦撞在这上面，它不是直接的擦撞在上面。So it actually collide on the iceberg itself. Okay. Now, on a normal condition, like say the temperature like this kind of condition, nothing would happen. It's really chill. Okay, you smash an iceberg, you get free ice cream, right? You have the iceberg that falls into a deck, and then you can just enjoy everything. It's just riding a tank. If you see the German tank or a tank, right? It just crushed everything, right? But that's not what happened when it's in the Atlantic Ocean. What happened is that there is a phenomenon what we so-called the ductile transition to a ceramic version. I won't get into the detail of that, but the overall is that the behavior of a normal metal that it's supposed to have a plastic deformation, it didn't. It actually turned into a ceramic material. Okay, very ceramic. So once it crashed, it shattered. So there was a small crack that opened up. Okay, small crack. It wasn't a big crack, by the way, small crack. So that small crack actually was vital. That actually sunk the entire ship. I don't think I have the drawing over here. So keep want to use the. So imagine this is the ship. Imagine this is the ship. You have a small crack like that. It kind of comes in, and it is this crack that is so vital that with time it actually starts propagating like that. And this is why normally when you see the movie or many pictures, it actually is a crack like this. It breaks through. All right, and if as a mechanical engineer, you can go ahead and calculate. The crack that opened up, that started propagating, was because due to the water that's continued to flow into the crack, and that opened up the crack vertically. So if it's cracked like that, it start kind of tearing it up. More water sunk in, the more cracks start moving up. The more water come in, the more crack up. And it is with this water, I forgot which water that goes into the cargo. So you have to think about, look, these kind of boats, it was designed as like these cargo hangers like that. That's like cargo, like each of these cargo, right? So imagine the crack, that crack over here. Right? So your water that flow in, right? So at that point, you have so many water pressure, it starts pushing into all the different cargo. And this on the left hand side is so heavy, it's sunk in. And then on the right hand side, it also sunk in as time goes on. So does that make sense to you guys? Alright. So the key to the fracture of material, is stability. The ability to hold crack, flaws, and concentrate stress. So that's vital, right? If you have whole cracks and flaws, you have a brittle fluid, right? So in brittle material, stress concentrating effect are activated by either immobility dislocation or lack of dislocation altogether. So you might want to. So these are two things why, if you want to answer why we have a brittle material, these are two. One is because you have immobility of a dislocation movement, right? So if you're a material background, I don't need to have to constantly remind you why we have plastic deformation, right? After passing yield is when dislocation starts moving, right? 对，当我们过项目强度就是差大概是什么时候，对不对？这是废话，对不对？所以 for those that doesn't know, it's important as a material scientist. So if the dislocation cannot move, we will have a brittle fluid, right? Second is that lack of dislocation altogether. So that's one of the consequences why we have a brittle fluid. Okay, so this is a brittle fluid, and then stop. So it's a very loud sound that you will see on a typical brittle fluid. Like it goes up, it doesn't have an yield, it just fails. Okay. Oh, so this is a whole point, man. We'll talk about that a little later. All right, so crack concentrate stress. So we're kind of zooming in and looking at its microstructure right now. Well, somewhat microstructure. So supposedly we have a specimen, right? And we're doing a tensile stress. So we have a sigma knot we're having, and imagine right now we have a small tip of a crack that's on the edge. Imagine, these are all moving, right? These are all moving at the tip. So it is understandable that we have a stress concentration, right? When we're pulling, the stress is all concentrated in this area, okay? I think that's very clear, right? So the stress over here is a lot higher when we do a loading stress over here, okay? So these are somewhat an empirical equation that describe the connection with the crack over here, that we have a stress concentrated at this tip, and the load we're giving on this specimen. Okay, so that equation is sigma maximum divided by sigma naught. So sigma max is the stress that is being concentrated over here. 就是比例的体重. Okay, divided by sigma naught equals 2a divided by r power of half. Power is 0.5. Okay, so a meaning that the fall size and crack length, right? R is the radius. So this equation actually what it does, it takes into the relationship the flaw size, the crack length, and the radius. Right? So if you have a more sharper radius, meaning that you're prone, you're more inclined to failure. Right? If you have a more circular radius, it's less likely to fail. Right? So over here, if you somewhat move the sigma naught over here, right? 你把这个位移一下. So this is a denominator numerator, right? So if you move the denominator over here, sigma naught times this over here, if you have AR and calculate it, you will know what is the stress maximum that's being concentrated on this area. Okay? So this is a empirical, 就是它不是一个叫什么？它不是一个解析解啊，它主要只是一个类似一个半径演示。Okay? Now this is one expression that you can do. So if you look at this, the fly stress, as I say, is F divided by A, and then adjacent to the crack tip, the local stress is greater than, this is just reiterating, okay? This is 重复我刚才所讲. So for ductile material, when the local stress, sigma, is greater than the yield stress, you have a localized yield stress, localized plastic deformation occur adjacent to the crack tip. For brittle material, the stress concentration caused the crack to grow rapidly, resulting in fracture when the local stress exceeds some critical stress. So I'll elaborate a little bit more further. So by the way, this is A. Griffith. He developed expression for the critical stress required for crack propagation, and was also one of the inventors for gas turbine as well as aircraft. So this is if you want to dedicate your life in fracture mechanics, you definitely know this person, A. Griffith, all the equation and stuff. So he's a well-known prominent person in fracture mechanics. He also was an inventor for gas turbine. I don't know if I tried to find a picture or image of him. I'm not sure if this is him person sitting on a gas turbine, but anyway, he's an inventor. So FYI for you guys to know. So these are the expressions. So one thing about these equations right now, with this equation right now, this equation, what it does right now is that then you don't need to specify the curvature of the crack anymore. Right? The crack is assumed to be automatically sharp. So with this equation, all you need to know is you need to know the Young's modulus, the surface energy, the pi, and the flaw size. Then you know the critical stress, right? So in other words, if I know the critical stress, I would know what's the flaw size, right? If I know all these modulus 就是材料的是因素，然后 surface energy 可以去查它，然后我也可以查出它的 flaw size。Okay, so so 这对你的研究到底有什么帮助 ？So what's so interesting about it? What would this help you for your research? Well, yeah, there's many things interesting, right? The important thing is about connecting the equation with your research, right? So perhaps you did a 4-point, you did a tensile test, you did a strength test, you did a 4-point, right? You get a load, right? So, and then you look at the microstructures, you see porosity. So the goal is, if you look at the microstructure, all you have to do is just find the largest porosity or crack in your specimen, right? And then it is that huge porosity that actually determines what is your strength of your material, right? 各位，你知道吗？我现在到底在跟你们说什么？你知道吗 ？So， 我们今天在看光学研究，不是都有我们做这个材料都有孔洞，这是不可避免的。所以大的孔洞跟小的孔洞，是谁决定今天这个材料会破损？是大的孔洞，因为大的孔洞它更容易应力集中，造成它破损。这个应该可以知道。所以我们今天看光学找个大的孔洞，量一下它的尺寸，把这尺寸带进去，然后再把马桶带进去，把surface energy带进去，我们就看出可以算出它的应力啊，对不对？那这时候这个应力跟你现在做的视点弯曲或是拉伸这个应力是哪一个高还是哪一个低？如果今天这个值它这个值远低于你的视点弯曲或是康拉强度的话，那就代表说你找到这个洞应不是最大的那个洞嘛。如果今天这个值是远大于的话，就代表你这个找的洞是最大的，就是说代表它影响你最后的强度。Does that make sense? Does it make sense to you? So why is it important for this equation? So I want to emphasize the importance about this equation is that perhaps in someday you'll do some mechanical testing, right? You will get 4-point bending, you do a tensile test. Tensile test is very common, right? You know tensile test, right? So with the tensile test, you'll get strength, right? You get the load, you get the stretch, right? Okay? Now, as a material background, what do you do the most? You look at the microstructure, right? So if you look at the microstructures, for any process you make for the material, you will always see porosity, right? There's always porosity, right? Now, if you agree, is that these porosity, the larger the porosity on a specimen, on the microstructure, the larger it is, the more heavy it will influence the final mechanical strength, right? So, for example, so perhaps, for example, we have a specimen, we have porosity like this here. So these are porosity. Okay, it gets small. So this, where do you think the failure will start? 它的那个破坏从哪里开始？
裂。
对，然后裂会先从哪里开始？从比较大的孔洞开始。So the failure will for sure start with the big porosity because the stress is being concentrated on the big porosity, not the small one, right? So interesting enough is today, all you have to do is put your specimen on a microstructure, find the biggest porosity, right? Measure that dimension, and then plug into this equation, and you calculate the critical stress, right? So that critical stress is telling you that that's the minimum stress for allowing a specimen to fail. Do you understand? So once you have the number, you can do a 4-point probe, and you get that stress as well. Stress, and then this stress over here. And then you can compare. If this value is smaller than the 4-point band or tensile stress, meaning that this porosity that we measure isn't the biggest. Alright? Now, if this value is bigger than the 4.0 or tensile stress, meaning that yes, this porosity is the porosity that influences your failure, right? Again, there's a lot of issues, a lot of conditions that influence your final mechanical strength, right? Perhaps there are some other factors, right? Maybe dislocation, strain boundary, etc. Right? But this is something very quickly you can kind of try to understand. Okay? The range is okay. All right. Let's have a break. 我们休息一下。